Dear students, today we'll see what do we mean by QPSK. QPSK means Quadrature Phase Shift Key. Now, before this, we should recollect what we have studied in BPSK and DPSK. So what we studied in BPSK was, we had a binary data 101010, and that binary data used to modulate a carrier in terms of phase. Whenever 1 used to come, it was 0 degree phase shift, and whenever 0 used to come, it was 180 degree phase shift. So it was varying between two phase shifts. That means for indication of one bit, we had a phase shift. For indication of another bit, we had another phase shift. That means for one bit, one symbol was representing. So the symbol rate and the bit rate used to be same. And when we came to DPSK, in DPSK we saw that initially we were encoding the data. We used to take the output of the XNOR gate and again delay it and give it back to the input. And with the main binary data and with this feedback, we used to take a XNOR combination, and based on that, whatever output we used to get, one bit, whatever output we used to get, that we used to use to modulate the carrier, again 0 degree and 180 degree. That means again one bit was representing one symbol. That means in BPSK and DPSK, in both the functions, one bit was representing one phase difference. One bit was representing one symbol. That means bit rate was equal to symbol rate, that is baud rate. So bit rate and baud rate was same. So there was limitation for the data rate, number of bits per second. Now to increase this number of bits per second, then we came to a concept where we were able to club two bits. Say if you are having 2 bits 0 and 1, then there can be 4 combinations in that. And the combinations can be 0, 0, 0, 1, 1, 0 and 1, 1. These were the combinations. So we will have 4 combinations. And for the 4 combinations, we will have 4 phase shifts. Say we will have phase shift of 45 degree. We will have phase shift of 135 degree. We will have phase shift of 225 degree. And we will have a phase shift of 315 degree. So in every phase shift, there is a difference of 90 degree. So we are having 4 phase shifts. Now, if you are having a phase shift, a particular phase shift, it is going to indicate a pair of bit. A pair of bit will indicate a particular phase shift. That means a pair of bit, which is also called as a debit. It is also called as a debit. So one debit, that is 2 bits, will indicate one phase shift. That means one symbol is indicating 2 bits. Another symbol is indicating another 2 bits. Another symbol is indicating another 2 bits. That means your data rate has increased. Your number of bits per second has increased, whereas your baud rate is same. Baud rate will be the number of symbols per second, but every symbol is indicating 2 bits. That means whatever baud rate you are having, the data rate will be more than that. That means this is an advantage. This is an advantage as compared to BPSK and DPSK. Therefore, this scheme in which we are going to use 4 different phase shifts, 45 degree, 135 degree, 225 degree and 315 degree, which will indicate 2 bits, which is called as debit. So 4 phase shifts, 2 bits each, they are going to indicate. So 4 phase shifts, because we are using 4 phase shifts, it is called as quadrature. Quadrature or quadriphase or quaternary. Quadrature phase shift key or quaternary phase shift key or quadriphase phase shift key. Quadriphase means 4 phase shifts you are going to use. And each phase shift is going to indicate 2 bits, a pair of bit. Clear? Now this will be the basic concept of what is QPSK, and this as compared to BPSK and DPSK, it is going to indicate, it is going to give you a higher data rate. and that is what the most advantage here is. Students, now we will see how do we generate a QPSK transmitter or QPSK signal. So the circuit which is going to generate a QPSK signal is called as QPSK transmitter. Now as usual, our input will be a binary data. Binary data will be in terms of 1, 0, 0, 1, anything. Now that has to be first converted into an electrical waveform, into a line coding format. So that binary data, whatever we are having, that will be converted into an electrical waveform by polar non-return to zero level encoder, whose work is that if there is a logic 1 as an input, he should give you certain plus voltage. If there is logic 0, he should give you certain minus voltage. So the output of this will be either plus voltage or minus voltage, depending upon whether your binary input data is 1 or 0. Then that electrical waveform is given to a demultiplexer. Now this demultiplexer is one which is going to separate these bits. The top channel will take odd bits and the down channel will take even bits. That means if the first bit is entering, whatever it is, whether it is 0 or 1, it will go to the top channel. It is called as B1. When the second bit is entering, it is the even bit, it will go to the down channel. When the third bit is entering, it will go to the top channel. When the fourth bit is entering, it will go to the down channel. Fifth bit, odd bit, will go to the top channel. Sixth bit, which is even bit, will go to the down channel, and this process goes on. One bit will go on top, one bit will go on top. And in both the channels, we are having product modulators, M1 and M2. These are called as product modulators. The other input to this product modulator is the oscillator frequency. So here we have named the oscillator frequency as A sin 2 pi fct. And here it is A cos 2 pi fct. So these are the two oscillator frequencies. What are the other inputs for the product modulator? Now, this output of the product modulator depends on which bit is entering. Say for example, the first bit which entered here was 0. Then the output of this product modulator will be minus A sin 2 pi fct. Similarly, if this bit which is entering is 1, then the output of this product modulator will be plus A sin 2 pi fct. Similarly, if you come to the down channel, if the bit which is entering here is 0, then the output of this modulator will be minus A cos 2 pi fct. And similarly, if the bit is logic 1, then the output will be plus A cos 2 pi fct. So, depending on which bits are entering, the sign of the waveform, the polarity of the waveform will vary. Either it will be plus or minus. In case of logic 1s, it will be plus, and in case of logic 0s, it will be minus. Now, those two outputs of product modulators are given to a summer, which is going to add them. That means what will happen is, at one time, one bit from here and one bit from here. So 2 bits, that means one debit, 2 bits. 2 bits waveform will get added here. 2 bits waveform will get added here, and the output will be one type of phase shift. Now that phase shift can be either 45 degree, it can be either 135 degree, it can be either 225 degree, or it can be either 315 degree. So any 4 combinations of phase shifts can come out, because this combination of a binary data can be 00, can be 01, can be 10, or can be 11. So there are 4 combinations of binary data, and hence you will get 4 types of phase shifts at the output. And because you are indicating the pair of bits as in terms of 4 phase shifts, that output signal will be called as quadrature phase shift keying, or quadriphase phase shift keying, or quaternary phase shift keying. So it is 4 phase shifts what is coming at the output, and every phase shift is indicating 2 bits, that is 1 debit. So here it is your QPSK signal which comes out for the incoming binary data, which is increasing the number of data bits per second as compared to your binary phase shift gain and your differential phase shift gain, that is BPSK and DPSK. This is the advantage of QPSK. So we are having 4 phase shifts as output, where every phase shift is going to indicate 2 bits. Students, now to support the QPSK transmitter action, you can use this table. Now in this, we have shown the initial binary data input, which is a pair of bits, which will be called as dbit. In that you can have odd bit and even bit. Then the second section we have shown the outputs of modulators M1 and M2. And third section we have shown what will be the phase shift in terms of degrees and radians. So say initially, if the pair of bit for the odd channel and the even channel, if it is 1, 1, one is going to the odd channel on top and one is going to the even channel on or down. If it is 1, 1, the output of modulators M1 and M2 will be plus A sin 2 pi fct plus A cos 2 pi fct. It will be plus A sin 2 pi fct plus A cos 2 pi fct. So whenever 1 is coming, it is plus. So this combination will give you a phase shift of 45 degree, that is in radians pi by 4. Similarly, if the combination of the input bit, 2 bits, that is pair of bits, if it is 0, 1, so the first one is 0, so output will be minus A sin 2 pi fct. And the second one is 1, so it will be plus A cos 2 pi fct. If you take this combination, the phase shift will be 135 degree, or it is 3 pi by 4. Similarly, the third combination, if it is 0, 0, the first odd bit is 0 and the first even bit is 0, then the output of modulators will be minus A sin 2 pi fct minus A cos 2 pi fct. This combination will give you a phase shift of 225 degree, radians it is 5 pi by 4. Similarly, the last combination, 1, 0, it will give you plus A sin 2 pi fct minus A cos 2 pi fct. This will give you a phase shift of 315 degree, in radians it will be 7 pi by 4. That means these 4 combinations of binary data, these bits, which are pair of bits, these 4 will give you 4 types of phase shifts at the output. So if there is a phase shift of 45 degree, then you should understand the data was 1, 1. If the phase shift is of 135 degree, then you should understand the data was 0, 1. If the phase shift is 225 degree, you should understand the data was 0, 0. And if the phase shift is 315 degree, then you should understand the data was 1, 0. So 4 phase shifts. So it is called as quadriphase or quadrature phase shift gain. This will be the phase shifts which you are going to introduce in the carrier, which is going to carry your data from one point to another in QPSK. Dear students, now we will see QPSK receiver. That is, we are going to demodulate a QPSK wave and we are going to extract a binary data from it. Okay. So the diagram for the process looks like this. Here the input will be a QPSK signal and there are 2 channels shown. On the top channel we are having correlator 1, down channel we are having correlator 2. And each correlator will have a product modulator and integrator, Now here, the signal will come here, a QPSK signal, a phase difference for particular 2 bits, and that will go to this channel also, to this channel also. Now, whichever channel matches with this oscillator frequency, here you can see oscillator frequency is A sin 2 pi fct. Here you can see oscillator frequency is A cos 2 pi fct. Whichever channel matches with the incoming waveform, that channel will take the cosine difference of these 2 inputs, and integrate that value for a signaling rate and use a voltage x1 output. Similarly, here also it will take the cosine difference of these 2 inputs and then integrate that value for a signaling rate and then gives a value called as x2. Now here you are getting output voltage as x1, here you are getting output voltage as x2. Okay, now that x1 will be compared with a 0 volt threshold in a decision device. Here also x2 will be compared with a threshold voltage of 0 volt in the decision device. If that voltage x1 is greater than 0, if that voltage x1 is greater than 0, that should come out as logic 1. If voltage x1 is less than 0, it should come out as logic 0. Similarly here, x2 is greater than 0, it should come out as logic 1. And x2 is less than 0, it should come as logic 0. Now both these are given to a multiplexer. That means one bit will come from here, one bit will come from here. And those bits will come as an output over here. Because one waveform will be of sine, one waveform will be cos. Sine a waveform, a bit will come from the top channel, and cos waveform bit will be coming from the down channel. And both bits will get multiplexed here, and output you will get 2 bits at one time. 2 bits at one time, depending on whether x1 is less than 0 or greater than 0, x2 is less than 0 or greater than 0. That means the output will be binary data in pair of bits. That means your QPSK signal is demodulated and the information is extracted in terms of binary data at the output. So this is your QPSK receiver, in which we have done the demodulation of the QPSK signal to get the binary data.